Hello, this is Team 10's retractable pool cover presentation. And for today's overview, we're going to be going through our design concept along with engineering analysis and how we're able to back up our concept, as well as creating our concept prototype, designing and testing, and our future improvements for. So traditional pool covers offer pool coverage, but make the space unusable. Drowning is a top cause of child injury deaths. A secure cover can help prevent accidents. Arizona pools face heat loss at night and overheat during the day. Covers help regulate temperature. Current covers are either expensive, which are the automated, or inconvenient, which are the manual ones, and few are load bearing. Our goal for this pool cover was to create an affordable, retractable, and load-bearing pool cover that creates usable patio space. Prototype uses a hand crank mechanism. Future designs aim for motorized automation. The current pool covers in the market are automated but very expensive, or not automated but much more affordable, not meant to have load-bearing capacities, and require a complex installation process.
So when looking at our competitors' products, we have three here up on the screen. In figure one, we have an automatic pool cover. As you can see, it's very expensive and hard to install. For figure two, it's a little bit more affordable, but it's manual. And for figure three, it's a long deployment time and it doesn't look great. And all of these also cannot have load-bearing capabilities. So for our project need, current in-ground pools inhibit the use of outdoor space while collecting local debris when not in use. There are also minimal options for affordable, automated, retractable cover systems. For our project goal, to develop an affordable automated pool cover that allows for easy deployment and retraction while enabling the usability of pool spaces. It will aim to keep debris out of the pool while being user-friendly and cost-effective. So looking at the objectives, some of the objectives that we came up with was affordability. We wanted to make sure that everyone could afford it and it wasn't too much. Storage, we wanted to make sure that it didn't take up too much space. Portability, we wanted to make sure that you can move it around. The aesthetics, we wanted to make sure that it wasn't an eyesore in your backyard. We wanted to make sure that it was easy to assemble and install, and we wanted to have it minimal deployment and retraction time. Looking at the constraints, some of the constraints that we covered and measured were the area covered of the pool by the cover, the deployment and housing time, 30 seconds, the prototype budget, under $800, applied weight has to withstand 300 pounds, has to withstand extreme temperatures, low and high, has to have a max deformation of 1.5 inches, has to have a maximum gap between the pool cover and the deck of 2 inches, and a time limit of 2 semesters, which we accomplished all of them.
So here's our concept generation where we came up with the ideas of using maybe a convertible car mechanism, a rolling track and slats, a scissor lift, or a hinge idea. To continue on, when trying to decide which design to go with, we scored them using AHP and a decision matrix. We decided on the rolling track slat concept, which is load-bearing slats rolling into housing, rolls along guiding rails, and is cable-assisted deployment to maintain tension. And then here is our chosen concept, which saw iteration before arriving to the final concept. Constraint changes, lower load-bearing requirement due to manufacturing capabilities and cost. The result is adding gaps plus links between slats.
And so here's where we landed with our final design concept. So our prototype, as shown in figure 12 in the isometric view of our final assembly, is broken down into three major components where our components consist of the pool cover itself, the spool, which we will use to basically retract and deploy the pool cover out onto the pool cover or onto the pool surface, and then the spool stands, which basically hold up that spool. Um, the pool cover is made up of the flow rails, the cover bearing surface, and the pulley mounts. The spool made of wooden rounds made out of plywood, a 2x4 crankshaft, and then we have metal pipe fittings and a hand crank. And then our wooden spool stands um, had ball bearings that mounted the spool, and then a locking mechanism for our hand crank after the retraction and deployment phases. And so through our prototype manufacturing process, here's a couple of our components that are key to the system's deployment and retraction. So at the top left, you have our flow rail joining piece. So this piece is a 3D printed piece out of PLA, which used nuts and bolts to basically join our flow rails at the center. Our length of our flow rail was 10 feet, but we split our flow rails into 5 feet sections to make the pool cover basically movable. And then in the bottom left, we have our cable guides. These cable guides basically kept the cable along the bottom side of the slats. As you can see on the top right, that's the bottom side of the uh, pool cover, and you can see these small cable guides along the left and right side of the cover. And then the two images in the center show the pulley mount. So the pulley mount ends at one side of the flow rail. Obviously, kind of just mounts that pulley, and the mount is actually also printed out of PLA, where it's bolted through the flow rails. And then in the bottom right, you can see the flat nylon mesh, which is also a part of that underside CAD view of the pool cover. And those go along the full length of the pool cover. And those basically hold tension as the pool cover is being retracted or deployed in our process. Additional manufacturing steps. One of our key components of our actuation for the prototype was the cable clamp, and the cable clamp can be seen in the four figures to the left. So the clamp was also a 3D print part printed out of PLA, where basically a top piece was embedded within a bore that was hand routed into the top of the end slat, and then a bottom piece was basically placed on the bottom side, the underside of the slat, and they were bolted together to basically clamp the cable and kind of create a fixed end at one of the sides of the clamp. And so this basically drives the deployment and retraction of our prototype. And the cable is basically in there based on a friction fit. And then we also have kind of our spool manufacturing. So as you can see in the CAD assembly, we have these what we call rounds. These rounds were CNC machined on a ShopBot CNC router. And so we did that by converting a DXF file from the CAD view into, to develop our G code. And then we created our spool, basically gluing and screwing these rounds together to get different stepped diameters to basically drive that actuation process. And then in the top right, you can see to actually fix our cables to the spool and drive the actuation process, we crimped the cables around these rounds.
In order to ensure that the final design promoted the constraints and that we had set at the beginning, we performed a series of engineering analyses. We started with the planks that we used as slats. We used ANSYS for this and applied a load in the center of the board in order to look at maximum deformation, maximum stress, and our safety factor. As you can see, the maximum deformation was 0.037 inches, which is less than what our maximum value was. And then equivalent stress and safety factor also show that the board is able to manage any loading that we would use as a functional space from humans or furniture, etc. Another point of analysis that we had to look at was the tension cable we were using in order to deploy and retract the cover. So we went ahead and looked at the two sides of the pulley where our force was split by 2. So we see 62.5 pounds on each side going into the cable. And then we were able to see that with the total weight and our assumptions that we were able to be good to go on this. And then continuing with the cable, we applied that the analysis in ANSYS again. We used a normal loading, a normal force loading, and then we saw that our maximum deformation was extremely small at 0.00007 inches, which matches what we needed with a safety factor of 15. So this was definitely usable for the factor, and we didn't need to worry about any failures during our building, and then any retraction and deployment actions. One piece that you guys haven't seen yet on the building is the motor, and the engineering analysis will expand why we did that. So as you can see in the figure with the motor requirements, we used the total weight that we had split into 125 pounds on each side with a total of 250 pounds. So with a radius of 7 inches, we ended up with a necessary loading from the motor, and then you can see the equations down at the bottom for the power that is required from the motor. And then the figure to the right shows our setup for the motor with the motor driver on B, and then part C being our microcontroller, or an Arduino Uno RC. Continuing with the motor, we had to test its function. So we needed a very large torque in order to pull this 250-pound cover. As you can see in the video on the left, we were able to achieve motion to the right or clockwise and counterclockwise motion necessary for both deployment and retraction. So that proves a proof of concept for using the motor. However, the video to the right shows the use of a tachometer, and then the figure on the bottom right shows applicable power or sample power set RPM. You can see in table 4 where we used an RPM range similar to what we would see, and then the output power. So you can see that we would only be getting 0.296 pound-feet, which is nowhere near what we need with this 250 pound.
All right, so because we weren't able to implement this DC motor, we needed to do some engineering analysis in order to design a hand crank that could produce enough torque with manual human operation. So we used a radius of 1.5 feet, which given our project dimensions was a reasonable size, and we wanted to verify that this would work. So we used a force value from literature of about 110 to 130 newtons that a typical person could produce. And then you'll see these low and high values for the torque and power. The low value is the required value based on the weight of the cover, and the high value is the value produced by a typical human. And so doing some simple torque calculations with the moment arm and the load amount, we see that a person would be able to produce enough torque and power to operate this cover. So next, we analyze the spool shaft stress. So what we're looking at here is basically the critical component of the spool shaft, which is the small steel pipe that runs through the journal bearings on the ends, because this is where the maximum moment and the minimum radius occurs simultaneously. So these are small hollow pipes made out of galvanized steel. And then running through some calculations here, we find that the maximum bending stress at this point is 9.5 thousand PSI. And using the yield strength of this material, which is about 35,000 PSI, we achieve a safety factor of 3.66. So this is within an acceptable range, and we were good to continue with our design. Next, we wanted to verify that the spool itself would not undergo excessive bending under the load of itself as well as the pool cover. So you can see on the left here in figure 31, we have a couple of free body diagrams uh, showing the load of the cover itself as well as the spool and the 2x4 through the middle there and the locations of all those forces. And then using some equations for maximum deflection that we got from Shigley's textbook, we achieved a maximum deflection value of 0.16 inches, which is small enough to be acceptable.
Okay, so once both the analysis and then the constant generation were completed, the group went into the testing phase. We did notice that we had three major failures that were kind of pivotal in solving for this prototype. The first one being the cable guide failure. So the cable guides are made out of PLA. Upon wrapping around the spool, were breaking due to the sheer amount of force applied by the metal cable. So to fix this issue, we use the guides. We use metal washers to secure those guides structurally to the boards more. So there's more surface area for the cable to apply force to, and that would be easier for the guides to not break. The second issue was the cable tension. So if both sides of the spool were not perfectly taut in the same amount of loading conditions, one side would deploy faster than the other, which would cause major issues. So in order to fix this issue, we had one person apply the same amount of torque or force to the cable in both or in the back in both directions. This also would make it more constant for both torsional stuff and allowed us to fix this issue as well. And the third would be flow rail assemblies alignment. Both the flow rails and the wheels were not mounted, and they tend to slip during retraction and deployment. So to fix this, we use glue on the wheels to secure them in place. And then for the flow rails, we use a 2x4 on the underside to secure them. And they also, so they wouldn't move during deployment. So in these videos here, the first one, basically, we did our first initial testing here. On the first one on the left, we did lose, it was too hard, so we had to implement a handbrake. The second one, there was a loss of tension in the cable. And the third one on the right here will be, there will be now, the tension was lost in this one. And so basically, so on the left here for the final testing, we had a first successful test. We went over the spool instead of under, which will cause us to allow less stress on the cover itself. Uh, Second one, we then added ourselves a stop for the handle, and then the third one was mounting our the lower part.
All right, so some things about our project that we can improve would be the material selection. So this was just a proof of concept. So we did use wood for this pool cover, which in general would not be the best material to use around something that's going to be near water. So instead, we would use enhanced weather resistance materials such as non-rusting metals or metals with a non-rust coat. And then we could also upgrade the flow rail wheels to metal instead of plastic, just so that they can support more weight and be more durable. We could also improve the steel cable grade so that it had reduced fraying and better weather resistance. Some mechanical upgrades we could include are reinforced mesh attachment on the underside of the wooden slats, and then also add a guided cable path on the spool to prevent tangling and fraying. And for functional improvements, we could implement higher torque motor for fully autonomous operation. We could also integrate a gearbox along with the motor to reduce the input torque and provide spool efficiency. And for the budget, we had $800 available. In total, we spent $629.65, which leaves us the remainder of $170.35. And the estimated cost for a full-scale pool would be between $4,000 to $6,000. So in conclusion, we had to reevaluate our initial objectives and constraints as we updated our design and our manufacturing. And this is just a proof of concept, and we had to perform frequent analysis and testing throughout this project. We did stay under budget, which is a bonus, and then we had to identify how to possibly upgrade the pool cover for the future. These are our references. And thanks for sticking with us this year.